Uniform circular motion, displacement, r is equal to a sine omega t plus p, a cos omega t plus q. So I like column vectors, as you know. I would have that as a sine omega t plus p and a cos omega t plus q. So it's the same sort of thing we had in the last lesson, but we've got the same value here and here, which means that when we draw this, then we know the center is at PQ, but this distance here is A, this distance here is A, and so it's going around in a circle. We can do a transformation and say that S is a sine omega t I plus a cos omega t j. So therefore S is equal to R minus pi plus qj, which just means that we move to a new set of axes where the motion is now around the origin. The velocity, just by differentiating, don't forget the chain rule, a omega cos omega t I minus a omega sine omega t j. The acceleration, a, is negative a omega squared sine omega t I, take away a omega squared cos omega t j. Notice that means the acceleration is negative omega squared s. If you take that and take out negative omega squared, what are you left with? You're left with a sine omega t and a cos omega t, which is s. Using a dot product, a dot v is equal to r dot v is equal to 0. And that means that the acceleration is perpendicular to the velocity, and also that the displacement is perpendicular to the velocity. Not surprising if you look at a point like this, where it will be travelling vertically upwards, but the displacement is measured horizontally. The period of the motion, t, capital T, is 2 pi divided by omega, something really worth remembering. And that's because if we think about omega t being equal to 2 pi, which is the period of both the sine function and the cosine function, and then just rearrange by dividing by omega, and we can see that that would be once around would be 2 pi divided by omega.